This is an industrial LED emergency light I was given to take a look at, and it's faulty. It didn't really last that long. If you look at the date, this has just been in storage since the whole lot of them have failed apparently, and it was clearly installed around about the April 2015 because they usually mark the installation date for the point you should change the batteries in the future. And this thing is quite neat because the front panel is just solid LEDs. It's based on 2835 LEDs, 2835, and the DC supply for them comes in at this end, and it's got a bus bar that goes down to the midpoint that it then jumps across in two links to provide power to the other part. But these LEDs are all wired in series strings of about 12 LEDs, and then all those series strings are put in parallel. And the only other thing in the front plate is the green charging indicator to show that the unit is charging the batteries inside. These batteries here, which are 3D size nickel cadmiums. The main circuitry inside consists of two sections. This is the main controller for the emergency light, and this is the LED driver. So in normal use, this unit can take a permanent feed so it can keep the batteries topped up, but it also has a switch feed for this in here, which is going to power the light and use it as a normal light. However, when I plugged this in, something in here was making loud fizzing, crackling, popping noises, and I decided to narrow it down. I disconnected one of the wires out of this and the popping, crackling stopped. So this is not happy at all. But then neither is this. This is the unit that's designed to handle the emergency charging and switching and powering of the lights. And in normal circumstances, it will have the main supply coming into it, and it can actually control it. The live for the LEDs also seems to be switched through that. I don't know if it's got a relay to switch this off if it ever kicks in, if it's permanent feed fails. But it also takes control of the LEDs directly, so it can disconnect the power supply here, and it can then generate the higher voltage to drive the LEDs itself, powered from the batteries. And I decided to give this a test. I took the battery pack out and I charged it in the bench power supply to give it a good boost to start off with. Then I put it back in and charged it up using this and then killed the power. And instead of the LEDs just lighting as they're supposed to, it started flickering and flashing continually. It wasn't stable at all. I'm currently surrounded by kitty cats here. This little kitty cat is just a neighbourhood kitty. It's called China, believe it or not. And the other cat is its kitten, little Hutchie. A kitten who had a bit of a rough upbringing. China's kind of like a stray, but locally adopted, and the kitten was brought up in sort of, well, not the ideal kitten upbringing, really. It's very feral, it's a bit shy, but likes company. It just likes, when I'm out here, it just sits there looking for company all the time. But yeah, so, oh, hold on, I've just been invaded by China here. So yeah, let's take a look at these individual modules. The reason I'm filming this outdoors on my lap is just because it's kind of big. It doesn't really fit in the bench. So we'll have a look at this and see what we can find. Oh, and then I'm going to try and resurrect it, because the voltage of these LEDs is pretty much the same as a typical high power LED. So I may be able to use a standard driver to actually run these. So we'll see what we can do. So let's start the power supply out of the unit. So this is a standard LED power supply, and this is a gin and tonic. The two go along very well together. This one takes its universal voltage, 100 to 240 volts, 47 to 63 hertz, and puts out, you can choose, and depending on the model, but this one's set for 36 to 42 volts, which ties in with the fact that the LEDs were multiples of 12, so that does sort of 3 volts for 12 in series, plus a sort of increase in voltage with the higher current going through them. And the current in this case is shown as 960 milliamps. Now, I've connected a standard LED to this. It's the standard tin chip LED, I'm sure it won't mind. And this is where I've found out that these heat sinks for solid state relays have the hole for the solid state relay on each side in just the right position that you can mount an LED diagonally on them with the same hole, so that's quite handy. So I've put a dab of heatsink compound, put this 50 watt LED, a crappy 50 watt LED on, and I'm just going to tilt that to the side so it doesn't blind us. Well, it might be this that blinds us, because this was making fizzing, popping noises when I tried it before. There was moisture present in the fitting. I'm not sure whether that was the cause of the fault in the first place, or it's been stored somewhere because once they were taken out, they were probably just put in a pile somewhere, so I'm not sure if that's the responsible for it, but let's try it out. This may go bang. If it starts fizzing and popping, I'm going to turn it straight off because I want to actually see what's causing that problem. So let's power it up. And it's lit. And it's not fizzing and popping. That's a good start. It might fizz and pop it randomly at some point. Let's measure the current. Let's measure the voltage across. This is going to swamp out completely, isn't it? It's swamping my vision out. Let's measure the voltage across that. Let's use proper glasses to do that, so I don't blind myself. Meter. Meter is visible to you, but not to me because I've got my dark glasses on now. So let's set this to 200 volts and probe that LED. 33 volts. Okay, righty-ho. I kind of want to know the current as well. Oh, I know how to measure the current. One moment, I'll just turn this off. And I'll get the little DC clamp meter on. We'll set this to 2 amp range. Is that going to be visible? Set it to DC amps, null it out, and this is supposed to be 960 milliamps. Oh, how accurate is that? Okay. Creeping up a little bit. 966. Yeah, that's pretty good. Yeah, that's very close. I wonder how it's regulating the current. So based on that, what is the output of this is? What does it say the power is? It doesn't. So the voltage, let's see. That was bring the big calculator. That was 33 volts times 960 milliamps, 0.96 amps equals, oh, it's about 30, just under 32 watts. So it must be a 30 watt driver then. Possibly a bit more with the higher voltage LEDs that, and the other panels. So let's open this and see what's inside. Let's disconnect this from here first. Disconnect these wires as well. Let's get this meter out of the way now. Is it going to be burnt inside? Has it been tracking? Let's discharge any juicy capacitors. Oops. Oh, it's trapped by the wire. Okay, I'm not seeing any capacitors on the input side. So what have we got? We've got the mains come in. There's a fuse, there's a metal oxide varistor, there's a common mode suppression choke, little tiny one. Some more filtering, another common mode suppression choke, the bridge rectifier. Some more big chokes. This thing is well filtered. Must be, up to a high standard. I'm not seeing any burnt marks. Oh, I'm seeing corrosion here. I'm seeing tips of rust here. Now, these things wouldn't normally just rust. I wonder... I get the feeling that when I turned it on, maybe there was water lying in this. And it made that characteristic arcing electrical popping noise that you get when the water's boiling. So I wonder if there's just water been bridging some of these contacts and it's gone now. I can see a slight discoloration at the bottom, but nothing major. And just a few dots of rust here, but most of the visual rust is on these, but there's nothing physically burnt that I can see, nothing that's been tracking other than through the water. Mega separation with a big beefy, this is what a class Y capacitor should look like. I like the fact they've got the separation between the MOSFET pins and over here between the rectifier. This is really nice. Any feedback? I'm not seeing feedback, I'm seeing a very thick insulation, the output of that transformer. Loads and loads of smoothing capacitors in parallel. And another little common mode choke. And more filtering. Yeah, it really does look quite well filtered. This little connector here looks like it is just in common with the output pins. Let's test that. I think that might just be a test connector. So I'd expect continuity from here to one of those pins. Yep. Yep, that's just in tandem, so it's just a test connector for when they're making them. Oh, as is probably that connector there. Yes, it is. It's just designed so they can plug on a test rig and test it in the factory. Okay, so I'd say that this unit is not to blame for anything. I don't know if the water's got in. Now, these are the screws that were holding it onto the case, and everything else was screwed inside the case, if I remember correctly. But these had been drilled through the plastic top, and they'd used this nylon washer to try and make it waterproof. I'm not sure if that's worked too well because there's corrosion all around that screw at that point. So it's possible that if water landed on top of the fixture, though it was supposed to be waterproof, it's wicked in, but you know what, it could have got in anywhere really. It's always hard to tell, and I don't know the location of these. I think it was a substation, not sure, or a storage area, maybe it's just the crack in popping was just a red herring. Maybe that's just something that water got in during storage. So let's go and look at the other bit now. So here's the main other bit of the light, and this is the emergency lighting module. And what this does is it's got this battery, it's got a charging circuit inside, and it's got a driver to drive the LED. And it can also take an input from the LED driver, which I'm guessing then it switches it through. Now the specification, it says on it that it can drive 2 to 20 LEDs at 6 to 60 volts. And then it says 320 to 43 milliamps. I wonder if that means that the more LEDs you add, the lower the current. You know, if it was just a couple of LEDs that was connected, it would be round about 320 milliamps, like say for instance 1 watt LEDs. But as the voltage increases across the number of LEDs, it's giving out a fixed amount of power, and the current drops accordingly. That would put this somewhere mid-range in that. So that would be round about, say, 150 milliamps or something like that. So let's try this out. I'm not sure what's going to happen here. Hopefully it's not going to go bang. I've got the LED connected. I've got this little indicator connect that shows the battery's charging. So theoretically I could just plug this in. I should mention that it was designed to get its ground through the casing. So I've actually pushed it onto a little spade that's punched onto the metal here. So let's see what happens. I can hear it humming. I just heard a relay click in. The green gallium phosphide LED has lit. It's an old school green LED, not very bright, but it doesn't have to be very bright. So that should be charging this battery now. I can certainly hear it humming. So let's unplug it and the LED should kick in. The LED has lit, but it's shimmering and flickering. There's a few chips out in the LED because it's a crappy LED. So let's see what current is going through this. It's very unstable. Let's see if we can get anything at all. So if I connect that up briefly and put this across. Turn this on to 2 amps. Oh, this isn't really going to be terribly visible. I'll turn it over like that then. Is that going to be visible? I think that's going to be visible. 0 out. Let's see what current flows. I'd guessed about 150-ish milliamps. It's not very high. It's flickering very dimly. And the original panel was flickering horribly. And it's only showing roughly 50 milliamps. It's not great. It doesn't look very happy. And this battery has got a modest charge in it. Rightio, let's open this unit up and take a look inside. So let's turn the power off. The light's lit because it's running off the battery, so if I disconnect this now, it should go out. make sure everything's disconnected so I don't get a little surprise. This is very much like the typical emergency light fixture. It's got a metal cover over it, which is probably going to be hellish to get off. They usually are. Oh, there we go. These are always hard to open. It's quite common for the inside, for the older school ballasts and things like that in fluorescent fittings. They tend to have these metal cases just because they're more heat proof. I should tuck that battery out of the way because it's good. These batteries, when I was young, well, it doesn't stop me doing it now either. I was working in a shop that I was refitting it, and I took some batteries out an old emergency light that were still in good condition and stuck them into a little tungsten flashlight I had at the time, and then proceeded to drop it from a modest height, and it landed and it broke. And the first clue that something was wrong was the smoke and the fact you could see the metal strap go inside the flashlight glowing red hot and the plastic all bubbling at the side. It was like a bit scary. So this, I don't see it. Let's disconnect that that ground connection. There's no obvious, oh there are, there's bits of rust. Okay. That's not going to help much. Oh, major corrosion in here. This thing has seen water, I'm pretty sure. I don't think it's electrolyte. Capacitor's all in good condition. This is just an ordinary transformer, a mains voltage, mains frequency transformer. That's kind of old school, but reliable. That really is probably killing the power to the it is actually, it's the contacts at this end are going through that to the output terminal that's switching the feed out to the remote ballast, the external driver. And likewise, this relay here must be switching the two poles between the internal driver, which I'm guessing is based on this choke here, this little inductor, and the external LED driver. The components inside, the little chip here is pretty hard to read. T2721. T2721. The transistor next to it looks like a MOSFET, perhaps? It's an international rectifier component. I can't easily read that. It's one of those laser etched numbers that's not actually. LR311, and there's two other digits, and they're not. It looks like 62311, LR31162, if that makes sense. There's two tiny little surface mount chips. This one is just marked 41H4, and then underneath that S14B, or is that S148? I think it's a B. And then there's another little tiny chip here. I wonder what these are for. S17B. It's odd. Okay, well I'm going to go and check what these are. I'm also going to clean this up and see if I can get this to recover. I get the feeling that the problem here is that water has got into this fitting, and it's the curse of waterproof fittings that water, if it gets into them, can't get back out. It's just that curse that, waterproof fittings, that is their biggest weakness. Connectors, light fittings, the more waterproof you make them, the more chance there is that if water does get in, and it does usually, then it's just going to cause problems inside by repeated sort of condensation cycles. It just deposits itself everywhere. That's still wet and squishy. Okay, I'm going to give this a clean up and see if I can trace those components out as well. So I'll just be back in a moment. So that's me giving it a clean up, and I've researched some of these components as far as I can see. I have to say, these components I didn't find what the 41H4 S148 was, nor did I find what the S17B was. I just did a quick search. Nothing came up instantly in the Google search. The MOSFET here is a hex FET. It's an LR3110Z, or Z if you prefer. And this component, this little chip down here, I thought it was going to be a switch mode type chip. It may actually be an op-amp 2721. That's the only thing I could find that was anywhere near close to that number. And it does kind of, the connection of the components, the pins, almost does suggest it is an op-amp, which would make sense because it's a very simple feedback circuit. Well, yeah, a very simple oscillating circuit with sort of localized feedback, the look of it, from this inductor. And that's why the output varies according to the voltage of the combined voltage the LEDs connected. So I've got the battery connected, I've got the LED connected. If I power this up, and noting that this is going to come live. Oh, I should mention, yeah, I used a toothbrush to scrub the isopropanol on. It was just about the best thing to do, really. So this is going to come live. This is probably why my channel seems to be affected by the same thing that Dave at EEV blog was mentioning recently. The, what do they call it? Restricted mode. I guess maybe my channel's too dangerous or something, because certainly it's been affected by recent activity. So let's power this up. And that's it now, effectively charging the battery. And it's enabling the emergency mode. The little green LED is lit. And if I disconnect now, this now, hopefully, the LED will come on. And this time it's not flickering, it is stable. So we can actually now, test with a meter and see what current's going through that. I reckon it'd be somewhere up to about the sort of halfway mark of 360 milliamps. So let's stick the little meter in, turn it on. Let's lean this down. Select that. Let's get the other cables out of the way so they don't affect the reading because it is magnetic. Zero that out. Right, okay. And now if I activate it, that should tell us how much current's going through. It's almost dead on 100 milliamps. Okay, slightly less than I was expecting, but I don't think it's a sort of linear output from that. So for that 100 milliamps, I wonder what current's in the battery. Right, okay, let's leave that disconnect. Let's disconnect the battery. Put that over to the side. Bring that and put it around one of the battery connections. So at the moment nothing is flowing, so I'm going to zero that out. Reconnect the battery at this side. And when I start charging it, this should show how much current the battery is being charged with, which is about 160 milliamps. So what about when it's running the LED? It's about an amp. Okay, so yeah, that works about right, because that's going to be close to about 36 volts across those LEDs. This is about a 3 volt, 3.6 volt battery. So the 1 amp does kind of relate with a slight loss to the 100 milliamp that's going through the LEDs by the time the voltage has been boosted up. So it's actually fairly efficient. Yeah. So the next thing I'm going to do is I'm going to try and get the light back up and running by wiring the original driver in now that I've cleaned it up, and just use it as a plain light. So I'll go and do that now. So I'm out in the hall on the floor just because, you know, it's a lot more room than on the bench, and I've got a LED work light here just illuminating what I'm working on. And I've taken the original flex out, which was 4-core, two live feeds, one switched and one unswitched for the emergency function. And I've replaced it with just standard 3-core flex. And I've removed most of the wiring in this unit. There was a lot on this tray here. And I've put the original driver back in because it's quite a nice driver. I was tempted to put that driver on here because it would have kept all the wiring from this terminal block on this plate and it would make it easier assembling light again. But I was concerned that this plate panel was going to get too hot because this has all the LEDs on the other side. But having said that, it doesn't actually get too hot. So The terminal block's the original. It's got the low voltage connectors coming from the LEDs going to that end of the driver. It's got a 240 volt coming to the mains in, and the earth is just connected onto this heatsink plate the LEDs are on. And if I turn this on now, you'll be able to see it. It spreads the dissipation over a very large area. The LEDs, oop, oh, that's bright. The LEDs are 2835, so let's, yeah, that's going to tame it down. That's actually showing a bit of flicker now, but it's going to be the very slightest bit of ripple because it does have proper smoothing. The LEDs are 2835s, there's 240 of them, there's 20 circuits, it's about an amp, it's about 50 milliamps per LED, but it's spread over such a large area, really it's spread over a massive area, that unlike a traditional fluorescent fitting where if you put an LED replacement in, it would be, you know, it would concentrate it all into a very small strip of LEDs that would get quite warm. This is just 30 watts and it's spreading over such a large area that the ambient temperature on this aluminium panel comes to about 15 above ambient, 15 degrees Celsius. So it's actually not too dramatic. It's a good way of doing it because it really does spread the dissipation. Each LED has a modest area of aluminium to spread the heat into. So it's actually quite an impressive light. It puts out a lot of light. So it will be useful just for general sort of workshop type use. It's been an interesting investigation.